Okay, guys, so let's talk about balancing equations. So, talked about a little bit yesterday how a skeleton equation does not care about how many atoms there are, it just cares about what the atoms are, what the reactants, what the products are. That's not going to work though in the real world. We need to balance our equations, and so let's do that. So let's look at just like a simple little example here. Let's look at how to make a bicycle. So I know there are more parts to a bicycle than this, but let's just keep it simple for the sake of simplicity. And so let's say that a bicycle is made up of a frame, wheel, pedal, handlebar. Those are the parts needed to make bicycles. So if you had an equation to make a bicycle, this would be your skeleton equation. Frame plus wheel plus pedal plus handlebar makes bicycle. However, you readily see that that's not exactly correct because you cannot make a bicycle out of those parts as they sit. You would need to add coefficients to some of the reactants to make your bicycle. And so everyone knows that a bicycle needs two wheels. You also need two pedals for your bicycle. And so you would add the coefficient 2 in front of the wheel and the pedal, and that would create your bicycle. A frame plus two wheels plus two pedals plus handlebars makes a bicycle. And so the important thing to remember here is that the only thing you can ever change is the coefficient. So don't ever try to change anything apart from the coefficient, the numbers that are in front of the chemicals. You cannot change this wheel into wheel subscript 2. It's not a wheel subscript 2, it's a wheel, and we're going to have two wheels. Does that make sense? Hopefully that makes sense to you. And so only change coefficients. If there's no coefficient present, then it is assumed and understood that the number is 1. Just like in algebra, if you have x, it's assumed that it's 1x. You don't have to write the 1 in front of it. Alright, so you might ask yourself, why do I care? Why do I need to balance the chemical equations? So this is the best picture of a science person I got here quickly. So the reason is because of the law of conservation of mass. That is why you balance chemical equations. And so remember, the law says that you cannot create or destroy matter. You can only rearrange that matter. And so an example, let's say that I had a simple little equation of hydrogen plus oxygen makes water. So in this equation, you ought to very quickly be able to decipher that there's something that's not equaling on here. Over here we have two oxygen atoms, and over here we only have one oxygen. There's a 1 here. We have one oxygen atom. So if we wrote the equation as this, then what we are effectively saying is that I began with two hydrogens and two oxygens, and I ended with two hydrogens and one oxygen. I destroyed one oxygen, and that would violate the law of conservation of matter. We can't do that. Okay, you can't destroy an oxygen atom. So that is why we need to balance equations. You do so by making sure that the number of atoms of each element that you start with and end with is the same. So the number of atoms on the left side equals the number of atoms on the right side of the equation. So here are some rules. Write these down. Get your pencil out, get your paper out, write these rules down. These are not exhaustive. A lot of balancing is going to just come with some trial and error and some practice, but here are your basic steps. First, you're going to write the skeleton equation down. If you don't get the right skeleton equation, then nothing else matters. For example, if you're writing the equation and you wrote H2 plus O makes water. Well, this is wrong because this is oxygen, which is diatomic, which must have a 2. And so you have to write the correct skeleton equation. You're going to count the number of atoms of each element of the reactants and the products. And I'm going to show you how I would do this initially. As you get better, you can go a little quicker at it. Note in both steps 2 and 3, if there is a polyatomic ion appearing on both sides of the equation, don't separate them into the elements. Keep it together as a polyatomic ion. That can happen 90+% of the time. Sometimes you have to separate them even when they're together on both sides, but usually you're good in keeping them together. Balance the elements one at a time by changing coefficients only. Never ever change subscripts. The moment you change a subscript, you are incorrect, unless you initially wrote it down wrong. And you'll probably have to go back and forth several times. It's okay to go left, right, left, right, left, right, even change something you changed before. That's no big deal. You'll get better at it, and you'll be able to kind of see ahead as you get better at it. So let's try one. Real simple. Hydrogen plus oxygen makes water. And so here's how I'd recommend, and again, you should be writing this down. Here's how I'd recommend doing this initially, is that you would draw a line underneath your arrow to divide the left and right sides, and then you list out your reactants and your products. So on the left side, we have how many hydrogens? We have 2. And we have how many oxygens? We have 2. On the right side, we have hydrogens that count up to 2 and oxygens that count up to 1. And so you can real easily see when you do this listing out that we don't equal out on both left and right sides. And so we need more oxygens. And so we're going to change the coefficient on the right side to give us 2 oxygens. And so to give us 2 oxygens on the right side, what coefficient do we need to put here? Remembering the coefficient is multiplied. It is distributed to everything in the formula afterwards. So if we put a 2 there, then that 2 gets multiplied to both the hydrogen and the oxygen. So the hydrogen count increases to 4, and the oxygen count increases to 2. 2 times 2 equals 4, 2 times 1 equals 2. Now that balanced our oxygens, but it unbalanced our hydrogens. So we have 4 hydrogens on the right and only 2 on the left. So we'll come back over to the left side and we'll change the coefficient in front of hydrogen. What do we need to put there? What times 2 will give us 4? Well, 2 times 2 will give us 4. And so that will change the count of the hydrogen from 2 to 4. And now we see we have equal numbers left and right on our equation. 4 hydrogens, 2 oxygens. We are balanced. That is your first example of balancing equations. All right, we'll do one more. I could do a bunch of examples here. I'm just going to do a couple. Really, truly, guys, you just need to practice these. It's very much, the more you do it, the faster you get at, the more efficient you get at. So I'm just going to give you a couple of examples, and then we're just going to practice them. So silver 1 nitrate reacts with copper metal to produce copper 2 nitrate and solid silver. And so let's do our equation. Remember, if you don't get your equation right, nothing else is going to work. So pay careful attention to getting your basic skeleton equation correct. So silver 1 nitrate. What does that 1 mean on the silver? Well, remember that 1 is the charge of the silver. Okay, and so Ag1+. And then nitrate, you should know that nitrate, recognize that as one of your polyatomic ions. That's NO3, 1 negative. You crisscross your charges, they're both 1, so that's going to be easy. You get AgNO3. So that's the formula for silver 1 nitrate. It's going to react with copper. Now, it's copper, so it's just the element copper, copper metal. You could put an S there afterwards, since it's the metal, and metals are generally going to be solid form. But we're going to ignore that for now. We're just going to do the equation. We're going to produce copper 2 nitrate. So once again, that Roman numeral 2 means that the copper charge is a 2+. The nitrate is still NO3, 1 negative. And so when you crisscross these, that 2 comes down over here. The 1 comes over. Put this in parentheses with the 2 on the outside. And you get CuNO3, 2. And solid silver. So we're just talking about the silver metal. So there is our skeleton equation. Again, you have to get the skeleton equation right. If you misplace a subscript, you write the wrong subscript, you're going to spend lots of time trying to balance an equation that you find impossible to balance. And it might be impossible to balance because you've written the wrong number somewhere. And so pay attention and do a good job writing your skeleton equations. That's why we did the practice yesterday on writing our equations. All right, so let's balance this. So let's start listing our elements. I just go left to right, so silver's first. So I'm going to write silver first, and then nitrate, and then copper. And I'm going to keep that same sequence on the right side, just so that I can look left and right real quick. So I'm going to go silver, nitrate, copper again on the right side, even though that the order is not the same on the right side. It just helps to not confuse you as you begin to do your numbers. So how many silvers on the right side? There's 1. How many nitrates on the right? I'm sorry, left side I meant to say. How many nitrates on the left side? There's 1. Don't put a 3 there. Remember that if you're talking about nitrate, and this is one of those areas of mistakes, nitrate is NO3. That's 1 nitrate. There's 1 nitrate. If you had 2 here, then you'd have 2 nitrates, but there's 1 nitrate here, so make sure you do 1. It's not a 3. And then there's 1 copper as well. On the right side, we have 1 silver. Now, how many nitrates do you have on the right side? That should be easy to see. There's 2 nitrates, and then there is 1 copper. And so, looking here, you can see that everything is balanced except for nitrate. We have 2 nitrates on the right, we have 1 on the left, so we're going to have to change the nitrates on the left. Again, what you cannot do is you cannot come over here, throw some parentheses around here, and stick a 2 out there to give you 2, because you've changed the subscript. The only thing you can ever change is a coefficient. So we need to have some coefficient out here that when multiplied in, it changes that 1 to a 2. Okay, and that's obviously going to be a 2. So we'll put a 2 there, and that's going to change 2 things. It's going to change the silver and the nitrate. You now have 2 silvers and 2 nitrates. Easy enough to fix this now. Go back to the right side where the silver is 1, and you can put a 2 in front of that silver, and that's going to change the silver count to 2, and now everything is balanced. So it's 2 silver nitrates plus 1 copper will produce a copper nitrate plus 2 silvers. And that would be your balanced equation. Then we're going to do one more. So zinc hydroxide plus phosphoric acid produces zinc phosphate plus water. So let's divide it up. Let's do our counts. So zinc, actually let's do this little helpful hint first. So if you have a hydroxide atom, which you do right here, there's your hydroxide. Remember, that's a polyatomic ion, OH1 negative, right? If you have a hydroxide on one side and it's not on the other side, but there's a water over there, then it's very helpful to rewrite that as hydrogen hydroxide, or HOH, because that way you can visualize your hydroxide on both sides and you can keep it together. So that's a real helpful hint. That doesn't always work, but it works most of the time. So just a helpful hint for you, makes it a little bit quicker. You can solve it without doing that. It just might be a little more confusing to solve it without doing that. So we're going to take that HOH right here, and we're going to rewrite that as, that H2O, and we're going to rewrite it as HOH. That's what we're going to do. Now, that allows us to keep an OH hydroxide polyatomic ion in our counts. So we have zincs, OHs, H's, and phosphates, PO4s, because we have phosphate on both sides as well. Okay? Now, do your counts. We have 1 zinc, we have 2 hydroxides, we have 3 hydrogens, we have 1 phosphate. So, again, be careful if you do this. Don't count these hydrogens here with those hydrogens. That hydrogen is part of the hydroxide. We've separated it out. Okay, on the right side, we have 3 zincs. Hydroxides, we have 1, and then we have 1 H in front of the hydroxide, and then we have 2 phosphates. Okay, and now we're going to start to balance it. So you can just go top to bottom in your little list here. We have 3 zincs on the right and 1 zinc on the left. So if we want to put a 3 in front of that, the 3 times 1 would give us 3. So a 3 over there. So this 3, once again, is distributed. The 3 gets distributed to the zinc. So 3 times 1 gives us 3 zincs. And it gets distributed to the 2 there. So 3 times 2 gives us 6 hydroxides. Alright, and so we have 6 hydroxides on the left. We have 1 hydroxide on the right, so we'll come over here and we'll change that. We'll multiply that HOH by 6. That changes our hydrogen count. Again, the 6 gets distributed to everything. So the 6 times the 1 hydrogen, and this hydroxide we've kept together, and the 6 times the 1 hydroxide, or there are 1s there. And so we have 6 hydroxides now, and we have 6 hydrogens now. Alright, and so now we're going to come back over to the left side and fix our hydrogens. We have 6 on the right side. We have 3 on the left side. So how do we get 6 out of 3? Well, if we come over here in front of the H3PO4, where we have 3, if we put a 2 there, then 2 times 3 would give us 6. So put a 2 there. That 2 gets distributed to the 3. So 2 times 3 gives you 6. It also gets distributed to the phosphate. Remember, this is a whole thing here. We have one of those, right? We have one phosphate. So 2 times the 1 phosphate, we'll change that to 2. And that actually balances it. You have 3 zincs, 6 hydroxides, 6 hydroxides, 6 hydrogens, 6 hydrogens, 2 phosphates, 2 phosphates. And so you're now balanced there. All right, again, practice, practice, practice. We have to just practice these. You'll get better at them. You'll get faster at them. Maybe a little bit difficult at first, but as you practice, as you begin to work on them, you'll find they'll probably be pretty easy.